Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
The first thing I want to do is give you a feeling for how much water there is on Earth. And what you're looking at is an image of the Earth with a hint of its topography, but without water in the oceans. All the water on the Earth in this illustration is gathered into this little blue marble that you see to show you the relative volume of water on Earth compared to the other constituents, mainly metal and rock. And so water is a very small component, but it's of course a very important component because it's a necessary ingredient for life, and since we're part of the living world on the planet, it's a very crucial part. Now, where does the water reside on Earth? The places where water is present we call reservoirs, and all of the principal reservoirs are shown here. It of course resides in the oceans. It resides in ice and snow, which I'm going to talk about more. It lies below the surface of the continents. It sits, of course, at the surface of the continents. That's the water that we are most familiar with. It's in the atmosphere and it's in the biosphere. But what you can see on this slide is that the 800-pound gorilla in the water story is the oceans of the world that have almost 96% of all the water. And as we know, the oceans are salty, and so the fresh water of the Earth is everything that is in the list below the oceans, and it's a small fraction. It's just a little over 4% of all the water on the Earth. Now, of that 4%, ice and snow make up 3%, or 3 of the total. So 3/4 of the fresh water on Earth is tied up in ice and snow. And perhaps surprisingly, water below the surface, we call this groundwater, is about 1% of the total. The surface water, which is the most visible, as I said, is really a small fraction of the total water on Earth, and then even smaller fractions are in the atmosphere and the biosphere. That has been pretty much a stable system, a system in equilibrium, but there are exchanges between the system that are going on all the time. For instance, if you look at the oceans, the units on this graph are in thousands of cubic kilometers per year, but for the moment we can just focus on the numbers. Evaporation is taking place over the entire ocean, and so the oceans are losing 434 of these units, but some of that falls back onto the oceans as rain, and so rainfall returns some of that to the oceans. But you can see that there's a deficit of 36 of these units. That deficit is in the atmosphere and it comes over the continents, and some of that falls as precipitation on the continents. So if we turn our attention to the continents, we have continents also are losing water by evaporation, but they get more than they lose from precipitation, and the balance, or the excess for the continents, is exactly the deficit from the oceans. And if we did not return that excess back to the oceans, we would gradually see a declining ocean. But in fact, that excess returns to the oceans through rivers and glaciers and groundwater that effectively go back to balance the ocean. 18,000 years ago, we were in the middle of the last ice age. And here's a schematic picture of what North America looked like 18,000 years ago. And you can see there is a huge ice sheet that covered nearly all of Canada, extended down into the Midwest of the USA and across New England. Greenland, of course, was covered. And at its thickest, this was probably 3 or 4 kilometers thick. And the center of that mass was over Hudson Bay. And Hudson Bay is actually created by the weight of the ice pushing down, loading the Earth's crust, and the Earth's crust sagging beneath the load of ice. And so even though today the ice is gone, the depression on the North American continent from the weight of the ice is still there, very slowly recovering from the removal of the ice. So given enough time, probably another 10 or 15,000 years, Hudson Bay will be gone, and the seawater that is lapping onto the continent there will be returned to the ocean. Now, this is a lot of ice, and the question that we have to ask is, where did the H2O come from to add that much ice to the continents? Well, if you go back to the list of reservoirs, there's only one reservoir that has enough H2O to loan H2O to the continents, and that's the ocean. So there's a long-term transfer, a long-term loan from the oceans to the continents of H2O during an ice age. And so if you take a look at the present-day distribution between the oceans and the glaciers and ice caps, this is what we had on the earlier list of where H2O resides. We have almost 96% in the oceans and 3% in glaciers and ice caps. But at the peak of the last ice age, 18,000 years ago, there was less water in the oceans. That means a lower sea level. And there's more H2O in the form of ice on the continents. Here's a graph or some images of the eastern seaboard of USA. Let me orient you. Here's New York City, Long Island, here's the Jersey Shore, Delaware Bay, here's Chesapeake Bay coming down through here. And the modern shoreline, which we all recognize, of course, is shown at the edge of the tan color, or the yellow color. At the time of the peak of the last ice age, 18,000 years ago, the shoreline was all the way out here. And that much of the continental shelf was exposed. And if all the ice that remains on Greenland and Antarctica were to melt, the shoreline would migrate to the green line and inundate most of New Jersey, all of Long Island, much of the New York and Connecticut coast, and much of Maryland as well. So there's big changes, of course, associated with big transfers of H2O between the solid phase that we call ice and the liquid phase of water. You can see on the topographic image on the right, the coastal plain shown in very smooth topography is where the sea level was about 3 million years ago during a high stand that was only 30 meters higher than the present day, but in the Pliocene geological period, all of this was covered with seawater at that time, and this is effectively covered with sediments that were deposited in that very shallow sea. Well, what's happening today? We're early in the year 2011, and we've just seen the announcement of the tabulation of the global temperatures for 2010. And the year 2010, according to NASA, was the warmest year since we've been taking temperatures around the globe, the warmest year in the historical record that goes back into the mid to late 19th century. The blue line here is the global average temperature gathered from thousands of weather stations on the continents, from sea surface temperatures measured by ships at sea, by floating buoys, by satellites overhead since around 1980. And you can see that there's a lot of what we would call short-term variability, lots of ups and downs from year to year in this record of Earth's average temperature. But you don't need to be a climate scientist to see that the general trend is up. And this is what we mean by climate. It's the long-term average trends of the weather. The weather year by year can be hotter, it can be colder, but the long-term trend, as I said, in this case, is definitely one that is upward. And so this is what we have been calling global warming over the last several decades. And you can see that particularly since the 1970s, it's been warming at a very rapid pace, and there's no end in sight. We'll talk more about what's leading to that, but nevertheless, this is what the reading of thermometers is telling us, is that the Earth is warming up. And that has consequences, of course, for the balance between ice and water. Now, there's been a lot of controversy about global warming in general, but about the so-called instrumental record, the record from the reading of thermometers at weather stations that you no doubt have followed with greater or lesser attention. It includes the swirl of emotion associated with the hacked emails at the University of East Anglia a little more than a year ago. It's on all the political talk shows and the like. And this instrumental record has not been without its controversy. But I'd like to point out that nature has her own thermometers, quite independent of human thermometers. And from my perspective, nature's best thermometer is ice. And in my book, I wrote this about ice, and I'll give you a moment to have a look at it. But the part that is particularly relevant here is that ice is a very neutral witness to climate change. And it, as you note, it's not burdened by ideology, and it carries no political baggage as it changes from solid to liquid. It just melts. And ice indeed is melting everywhere on Earth. In the Alps of Europe, in the Rocky Mountains of the USA, and in other places around the world, mountain glaciers are receding. Let me show you some pictures. Here in Switzerland, the Rhone Glacier in 1850. It was this big tongue of ice that came from an upland valley down a slope and had this big globe of ice in the valley that you can see here. And this was in 1850. And by 1927, here's the Rhone Glacier. The tongue of ice coming down from the uplands is still there, but the big globe that was down here is gone. By 1981, the slope is now free of ice, but there's still ice in the upland valley. And I'm going to show you a view from this little hotel right up here, the Hotel Belvedere, in 2007, that's the view. The upland valley is now free of ice. And just a reminder of what it looked like a century ago, here's a postcard showing the same view, but the valley is full of ice. This is Glacier Bay National Park. I'm sure that some of you have had the opportunity to go there on small cruise ships. It's a wonderful trip. This is I think the McBride Glacier, or the Muir Glacier, I'm not quite sure. This is a picture in 1988, and you can see where the glacial front is. But in 1966, it was out here, and these sediments at the mouth of the valley are the recessional moraine of the glacier in 1966. And so it's retreated several kilometers in just that interval of time. In the Beagle Channel of southern Chile, in the southern hemisphere, this is a glacier that is coming off the South Patagonia ice field, and in earlier times it came all the way down to the Beagle Channel. All this area of clean rock was covered with ice in 1835, and we know that because Charles Darwin sailed on his voyage of the Beagle. This is named for his ship, the Beagle, HMS Beagle. He remarked in his journals that the Beagle Channel was clogged with ice and that glaciers were extending all the way down to the water, and that discharging of icebergs made navigation a little bit dicey as they made their way through the Beagle Channel. But today, you don't find any of that ice in the Beagle Channel. Where you do see it is still way up on the hill slope. The Baltoro Glacier is a very famous one, and it's one of many. There are thousands of glaciers in the Himalayas and the Tibetan Plateau. And these glaciers are also undergoing shrinkage and ablation. Here's a picture in the Himalaya of what the upper picture was taken in 1921 and the lower picture in 2009 from the very same perspective. And of course, you can visually see that there's been a retreat of the ice, but what you don't appreciate quite is the thinning of the ice as well. And the red arrows are pointing to exactly the same place. And the lower one shows that the ice is further down the hillside now, and about 110 meters of thinning of the ice in just this last century. So the consequence of that and of the melting of the Andean glaciers is that major rivers that provide the agricultural water, the municipal water for sewage and the like, domestic water, for as much as a third of Earth's population derives from these mountain glaciers. And here you can see in Asia, the Indus River, the Ganges, the Brahmaputra, the Mekong, the Yangtze, the Yellow River, all the major rivers of South Asia have their headwaters in the Himalayas and the Tibetan Plateau. And there are probably anywhere from 20 to 30,000 glaciers in this region feeding these streams. And these glaciers are receding, they are thinning, they are melting. And the projection of when we might lose these glaciers is certainly not immediate. But when it does happen, because of its consequence for so many people around the globe, losing the mountain glaciers of Earth has really severe social impact on the water supplies that so many people depend on. Well, I want to now leave the mountain glaciers behind. Not that they have any insignificant importance, as I've already mentioned. But I want to talk next about sea ice. Now, what is sea ice? Sea ice is simply seawater that gets frozen. And I'll show you a picture of what sea ice looks like. This is a view of the Arctic Ocean, and you can see big pile of ice on Greenland. This is land ice. But the Arctic Ocean is annually frozen over during the winter, and then it breaks up some in the Arctic summer, and then freezes over again in the winter. There's a cycle of freezing and breakup in the Arctic Ocean, but this particular view is in September, which is the end of the summer. And so even after a whole summer of warming and breakup, there's still a very substantial amount of sea ice in the Arctic. And it's this sea ice in the Arctic that has made it so difficult to travel from Europe to North America and Asia across the Arctic Ocean, the so-called Northwest Passage that so many explorers gave their lives looking for, that the existence of sea ice, even at the end of the summer, has always been a barrier to trans-Arctic ocean transport. Well, the sea ice is changing. Now, sea ice is very different than land ice, principally in thickness. Greenland is very thick. It has as much as 3 kilometers of ice piled on high, whereas sea ice, here shown in the foreground of this illustration, sea ice frozen from seawater in a year will achieve a thickness of about 1 meter or 1.5 meters, 3 to 5 feet of thickness. And so compared to the kilometers of thickness on Greenland and in Antarctica, sea ice is a very thin sheet. And you get that impression just looking at this sea ice in the foreground versus some land ice in the background. Now, sea ice in the Arctic Ocean has been diminishing in the summertime. A look at just a map of the extent of sea ice at the end of the summer in the Arctic is shown here. In 1980, it was still very similar to what I showed for 1979 in that satellite view. But the extent of sea ice at the end of the summer in 1980 is shown by the light blue coloring here. And by 2005, it had shrunk to this intermediate blue. 2007, the dark blue here. And what this does is that it changes the thermal situation in the Arctic in a very important way. Because ice is white, effectively, and ocean water is dark. And as you lose the white surface, which reflects a lot of the incoming solar energy back to space, and replace it with dark ocean water, which absorbs the incoming solar radiation, then you're storing a lot more heat in the ocean water of the Arctic as it opens up in the summertime. Now, it does refreeze in the winter, but it freezes later in the season because it's warmer. It doesn't achieve as thick a sheet of ice as it would in colder times, so the ice is thinner. It is weaker and breaks up earlier in the springtime, and it becomes what we call a positive feedback that is just now leading to shrinkage of sea ice at the end of the summer. Here's a graph of that at the end of the Arctic summer. Since about 1980, the reason this graph starts in 1980 is that's when we have satellite synoptic photos of where the sea ice is. But you can see that, yes, indeed, there is interannual variability. There's some years there's ups and some years there's down. But once again, the long-term trend of end of summer sea ice is there's less and less of it in the Arctic Ocean. Now, it's important, again, to pay attention to the thickness of the ice, not just the aerial extent, but the thickness. Here's a collection of 4 depictions of the upper left here is the average sea ice over 1981 to 2000 in terms of its thickness, with the dark red being what we call multi-year ice. It's been around for more than 2 years. It didn't get broken up in the summer, and then gradually extending out into the orange and yellow, where the yellow is first-year ice, which never is more than a meter or a meter and a half in thickness. The multi-year ice can be 2 and 3, and even in some cases as much as 5, or even in a few cases 10 meters thick. Still much thinner than Greenland, but nevertheless, the thicker ice is more durable ice. It's harder to break it up. So this is what the average thickness and age relationship is for the average from 1981 to 2000. 2007, as I already pointed out, the extent of it was much diminished at the end of the summer. In 2008, there was more sea ice, but it was more first-year ice. It was more of this yellow ice. And in 2009, you can see it's a blend of first-year and second-year ice, and very little of the old multi-year thick ice remaining in 2009. Now, I said it refreezes in the winter, and so here we're looking at end of February, which is nearly the end of the winter, not quite the end, but here we're looking at the refreezing of the Arctic Ocean. And you can see that the entire ocean is covered with ice, and ice extends down the side of Greenland and through the Davis Strait up here, and through the Bering Strait and out into the Pacific Ocean. And so there is the refreezing, but the average age of the Arctic Ocean ice in this baseline period was some old ice sitting here north of Canada and younger ice on the Asian side. But by 2009, the older ice is greatly diminished, and the young ice is the dominant form of ice, the thin ice. And this, as I said, come the next spring and summer, is easily broken up and lost. So in the big graph down below, you can see that gradually there's an increasing amount of young ice at the end of the winter and a decreasing amount of the older and thicker and more durable ice. Now what about, well, before leaving the summer sea ice, I might point out that the trends of summer sea ice loss, if it continues, it's losing summer sea ice at about 10% of its area every decade. And so if that trend, this is the long-term trend, this is the climatic trend, not the year-to-year variability, if that trend continues, by mid-century, we will see an open Arctic Ocean in the summertime for the first time in human history. Already there are big stretches that are without sea ice, but if this trend of summertime retreat continues, we will see an ice-free Arctic Ocean during the summer. Now what about what's happening to the extent of the winter sea ice? Even though I've already told you that it's getting thinner, we're also discovering that its areal extent is diminishing, although not as fast as the summer's ice. Here you can see the same 20 or 30-year period of winter sea ice. It's of much greater extent, of course, but much of it is this thin first-year ice. And even the extent of this winter sea ice is diminishing at around 2.5% per decade. And this has to do with the fact that the oceans have been getting warmer in the summer, and so the ability to freeze it in the winter is diminished. Well, this changing thermal regime in the Arctic is spreading to the regions around the Arctic. It's spreading further south in all directions. And what's being affected is the area of the globe that is in the condition of permafrost, which means that the temperatures in the subsurface are below the freezing point. Any water that's present in the sediments or in fractures will be in the form of ice. And the colors here show the areas that are what we call continuous permafrost in the dark purple, and then in various stages of discontinuous or patchy permafrost further south. But there are big areas of the globe that are permanently frozen, except for the summertime, when a very thin zone at the top of the permafrost melts a little bit. This is called the active zone, and the upper meter of the permafrost will get soft and mushy down several tens of centimeters, maybe a meter, and then in the winter it will refreeze. Now, while it's soft and mushy, in the summer you can't travel across it. But if you've watched this television series of the big trucks rolling across the frozen terrain, it's not just ice, much of it is over the permafrost terrain. And the times of the year that there's transport allowed or possible across the permafrost is diminishing because of the warming of the Arctic. Here's a graph that shows the interval of time in terms of the months of the year when you can travel across the permafrost because it's frozen. And back in the mid-1970s, it would be somewhere from November through May. But what we've observed is that the permafrost does not refreeze until later and later in the season, And now it's sometimes actually into January before you can travel across the frozen permafrost, across the tundra. And this is just one more example of nature's own documentation of climate change, the narrowing window of possible transport across the Arctic. Now, what that signifies, of course, is that we are undergoing more and more melting or thawing of the permafrost. And one of the physical characteristics of the phase change between ice and water is that the ice phase of H2O occupies more volume than the water phase does. That's why if you leave a bottle of milk out on the doorstep, of course, no one has their milk delivered to the doorstep anymore, but it used to be that if you failed to bring it in, the cap would pop and the milk would be in a little milk column sticking out the top of the bottle. But in the transition back from the solid phase to the liquid phase, there is a decrease in volume. Water occupies less volume than ice. And so what that has done is led to a disruption of the surface of the tundra and has created a series of depressions that are now occupied by water. And here's a picture, an aerial picture in northern Siberia of a number of these lakes that are created by the subsidence in areas where the permafrost has become thawed. And the origin of this word thermokarst, the root there of karst is related to the formation of caves and depressions and sinkholes are a good example in limestone where groundwater dissolves limestone and creates collapses. Here, thermokarst is saying that you accomplish the same creation of sinkholes and depressions, but it comes about by thawing of the permafrost. Well, this destabilization of the land surface has important consequences for terrain that has succumbed to the thawing of the permafrost. Here's a couple of examples of the infrastructure disruption that can happen as the volume of the terrain changes as the H2O goes from solid to liquid. I'm going to run through a number of pictures here that show examples of this in other settings. Here's a place, Dawson City in the Yukon, where some of the old structures are falling down because of the thawing of the permafrost. Here's another example in Dawson. And there's a phenomenon called drunken trees, where the trees are tilted at odd angles. And this, of course, is because the permafrost has thawed and the stability of the root system has been affected, so the trees are tilting in all different directions. Now, this phenomenon of change of volume in the terrain as to whether it's frozen or not was a very important consideration in the building of the Alaska pipeline, the oil pipeline from the north slope of Alaska down to Valdez in the Gulf of Alaska. So you can see the pipeline here running from Prudhoe Bay to Valdez. And much of the terrain that this passes over is permafrost. And the oil that comes out of the ground is very warm, and because the interior of the earth is warming up as you go down. And so to bury a pipeline and transport warm oil through it would lead to destabilization of the permafrost. And everyone said, don't bury the pipeline. You'll have to build it overland. And so for those of you who have ever visited the Alaska pipeline, driving north from Fairbanks to Prudhoe Bay, you can see this kind of a situation. The pipeline is elevated. It's up on platforms, and these are high enough so that wildlife can pass beneath it. But as you might guess, it's a very inviting target to anyone with a high-powered rifle, and there have been many small punctures of this that have led to so far only minor spills. It's also an obvious target if one wanted to be a terrorist. You've got a huge distance of this, many hundreds of miles of this pipeline snaking over the surface of the Earth. And there's a road that runs right along next to it that has maybe 10 vehicles a day. And so, but it's perfectly accessible. In the summertime, it's an easy road, an easy drive north. So there's a lot of infrastructural instability that's associated with the thawing of the permafrost. And there's a map where the red areas show the areas that are thought to be most vulnerable to permafrost thaw by mid-century. Now, there's yet another feedback that is becoming active in the Arctic. I already talked about the positive feedback of the albedo effect of replacing white ice with dark seawater and the warming of the Arctic because of that. But as the Arctic is warming, both at sea and on the adjacent land, another phenomenon is taking place, and that is the release of methane. Methane is the principal gas in what we call natural gas, and methane is itself a greenhouse gas. And so as methane is being released by the thawing of the permafrost and other deposits of methane, you find that methane is making its way into the atmosphere. It's an interesting phenomenon. Here's a methane passage. If you wanted to cook hot dogs or marshmallows, it would be there. And on a broader scale, here's a marine geophysical survey that showed plumes of methane bubbles rising from the seafloor in the North Atlantic Ocean just west of Svalbard. The extent to which methane release is changing climate is not real understood yet because we don't know, maybe methane was escaping for a long time anyway. Maybe it isn't just climate change. But there's no doubt that as people start to study methane release now, you're seeing it more and more across the Arctic. Well, I want to turn now to the big ice, which is Greenland and Antarctica. So here you can see Greenland over here. As I said, it has some 3 kilometers of ice at its thickest, and Greenland is warming up too. In this depiction, the pink was the extent of summertime melting that took place on Greenland 20 years ago. And it's largely confined to the southern areas and to low elevations. And this is something that every year takes place, just like the Arctic sea ice changes from summer to winter. The Greenland ice at low elevations and in the southern areas would likewise undergo some melting at the surface and then refreezing in the winter. But the area of Greenland that is now undergoing melting has been climbing higher and higher, and now there's melting at all latitudes of Greenland, even in the far north. You can see that it's well above the 2,000 meter line, which is this little faint line right here. So you can see that melting is well above 2,000 meters in elevation. And what that is producing are big meltwater lakes sitting up on the ice sheet on the top of Greenland. And these lakes are, as you can see, there's little channels. Some are leading into the lake, but sometimes the lakes find fissures and cracks in the ice that they leak out through. And here's an example of a fissure that is draining some of the meltwater, summer meltwater. And this glacial meltwater plummets all the way down through the ice sheet to the base of the Greenland ice sheet and the rock beneath it. And it's lubricating the glaciers as they are spilling off of Greenland. And so we're seeing an acceleration of glacial loss from Greenland because of this lubrication effect of the higher elevation melting finding its way down to the base. Here's the Jakobshavn-Isbrae Glacier in the northwest part of Greenland. It's been retreating since 1850, but it's been particularly retreating rapidly in this last decade between 2000 and it's even a little further along today. But it's retreated some 10 kilometers or 6 miles in just the last decade. This particular glacier drains about 10% of the ice loss from Greenland. Now, what about the Antarctic, the big pile of ice? Here's a picture, composite from many satellite photos of Antarctica. It's effectively ice covered, although up close there will be rock. The South Pole sits just about here, and this is in a sense what North America must have looked like 18,000 years ago. And so if you want to get a feeling for what Ann Arbor looked like, or New York, or Chicago 18,000 years ago, you can take away the human structures here, just one broad polar plateau of ice. This is the research station at the South Pole, and this long line here is an airstrip just on the snow by which people and supplies come in. This polar ice slowly moves downhill away from the polar plateau in huge glaciers, flowing rivers of ice. Polar plateau is in the background, and eventually it reaches the sea. And although this next picture is not from Antarctica, it demonstrates what happens. You have this spillage of glacial ice, and it's really behaving very much as a liquid, a very viscous liquid, something like, pancake batter spreading out onto a griddle. And some of this ice will be sitting on the seafloor, but eventually it spreads out far enough to be floating. And it's the floating sea ice that you can find all over the periphery of Antarctica, indicating this spillage of glacial ice off of the polar plateau. So in the Antarctic, these light blue areas, this is the Ross ice shelf here, and this is in the Weddell Sea, a big ice shelf, and up along the Antarctic Peninsula, pointing up towards South America, this ice shelf on the east side, and there's some smaller ones on the west side. But these are these spillage zones of glacial ice that have come off of the continent. Now, this has been a natural process, but what we're discovering is that these big ice shelves are becoming unstable, particularly by the effect of a warmer ocean underneath them. They're being eroded and weakened from beneath. And so I want to point out one of the big breakups of recent years was up here on the Antarctic Peninsula in what is called the Larsen Ice Shelf. Here's a satellite photo, so the distances here are probably around 200 kilometers in each direction. And the peninsula rock and mountains are shown here, and then this is the floating ice shelf over here. And in a period of just 5 weeks, a big chunk of ice about the size of the state of Rhode Island broke away and is being washed out to sea. Elsewhere along the Antarctic Peninsula, we're seeing breakups of the ice shelves. This is on the west side, the Wilkins Ice Shelf. And let me tell you that these ice shelves, they're really big ice. The title photo that I used for this lecture shows you what some of that ice looks like. And this, of course, is the part that you see above the water. A lot of the icebergs are below the water. Compared to an oceanographic vessel, you can really get an impression of what the ice is like. Well, I want to now come to the final topic, which of course is the rise of sea level associated with the changing ice situation on the globe today. Sea level rise is not something of the future, it's already rising. And here's a graph of sea level change over the last century. And you can see that here we're simply looking at tide gauge records from around the globe. That's what all the thin colored lines are. But the average of that, of course, is unmistakable and upward. Sea level is rising, and since the 1980s or so, we also have satellite altimetry that is giving exactly the same trend, so there's no bias to this data. This is a rise of sea level in the 20th century of about 4 inches, or 8 inches, excuse me, about 20 centimeters. And, but it's accelerating towards the end of the 20th century, and it's almost twice as fast today. And this has serious consequences. There are places in the world that are very low-lying. This is the Maldive Islands, the capital city. I think it's called Male. The Maldives have the distinction of being the lowest country in the world. There's no place in the Maldive Islands that are more than 7 feet above sea level, and most are considerably lower. And so you can see already there's a seawall built around the city here to protect from storm surges. But low-lying islands, not only in the Indian Ocean but the Pacific, are particularly vulnerable to sea level rise. But it's not just remote places. Sea level rise in the 21st century, I predict, will be on the order of 1 meter or maybe even 2 meters. That's somewhere from, on the order of 3 to 6 feet. What would that mean for terrain that we're familiar with? Well, here's what a 1 meter sea level rise would mean in the Gulf Coast area and the Atlantic coastal plain. The areas in red are areas that would be inundated by a 1 meter rise of sea level. If we think New Orleans had problems with Katrina, all of South Louisiana would be permanently underwater. The Everglades of South Florida, many of the barrier beach communities of the eastern seaboard would be lost. In the west, this is San Francisco Bay. As you know, much of San Francisco Bay is reclaimed land anyway that's barely above sea level. The airport at San Francisco is just right there at sea level. And what perhaps you don't appreciate is that going up towards Sacramento, here's Sacramento, it's really low terrain all the way up the Sacramento River. And so if you look at San Jose and a lot of the beachside communities, both on the East and West Bay, would be underwater with 1 meter rise in sea level. In Europe, 1 meter in the Low Countries, the Netherlands, and further north all the way up into Denmark, and to the south, and of course in the UK, along the eastern seaboard. And then in Asia, Tokyo Bay, 1 meter rise in sea level. And I should point out that the white on this graph is population density. And so we're talking about areas with high population density that will be inundated with a 1 meter rise in sea level. Now, as I mentioned, in Greenland and West Antarctica, there's the equivalent amount of ice that could raise sea level 6 to 7 meters if we would lose the Greenland or West Antarctic ice. Now, what would a 6 meter rise in sea level be? Well, you already have seen 1 meter. I'll just give you a brief look. 6 meters of rise in the Gulf Coast and the Atlantic coastal plain would be a major rearrangement of the geography and the social structure of our coastal states. Now, worldwide, this is a graph that shows you the population of the globe that would be displaced by given amounts of sea level rise. And the 1 meter of sea level rise, which I think is a very likely number for the end of this century, will lead to the displacement of 100 million people who live essentially at sea level. And a 2 meter rise is almost 200 million people. And as you can see, the higher the rise, the more are displaced. The social upheaval of trying to deal with 100 million climate refugees around the globe is profound. It's not something that we have ever faced, and I think it's safe to say that the world is not prepared infrastructure-wise or sociologically to deal with that many climate refugees. Now, when will all this happen? Here's my best estimate of the timetable. In the next few decades, most of the tropical and temperate mountain glaciers will disappear with the attendant problems in water supply for the people who depend on that. There'll be an ice-free Arctic Ocean in the summer, which will open up great interest in exploration for minerals, for fishery, for factory fishing ships going in there, and for territorial issues between the nations that surround the Arctic. And then the shallow degradation of the Arctic permafrost with its structural instabilities that I mentioned earlier. By the end of this century, sea level will rise between 1 and 2 meters, 100 to 200 million climate refugees. And if nothing is done to mitigate the climate change that is underway, the Greenland ice will reach a point, not that the ice will be gone, but that there's nothing we can do that will prevent it from gradually going into the sea in the centuries following. In other words, the system will have been endowed with enough energy and it will have enough inertia that even if we were to go cold turkey on our use of fossil fuels, Greenland would still have been moved over that tipping point. And so it's a very important thing to try and prevent that. Now, while I say that these are issues that seem very momentous, if you look at what the human population is doing year by year, this is carbon dioxide concentration, a greenhouse gas, the most important greenhouse gas, has been climbing ever since we've been measuring it in 1957. And the rate at which it's climbing in the atmosphere is increasing. In other words, there's an acceleration of the greenhouse gas concentrations in the atmosphere, which means that the temperatures are going up even faster. And so this is a warning sign in a sense that something should change, or else we're going to have serious consequences. And putting this into a long-term context, I'm going to change the time scale dramatically here to go back several hundreds of thousands of years. What we know from the record in the Antarctic and Greenland ice is that carbon dioxide in the atmosphere has fluctuated naturally in and out of the ice ages, and with a roughly 100,000 year period. So 100,000 years ago, or 120,000 years ago, we were in another warm period, and 100,000 years before that, another warm period, and another warm period, that in each case declined into a low carbon dioxide and low temperature environment that we call an ice age. And our last ice age reached its maximum, as I said, 18 to 20,000 years ago. But throughout that period of time of ice ages coming and going, and the big climatic shifts that we think of an ice age and an interglacial period, that the carbon dioxide oscillated only between about 180 and 300 parts per million in and out of all that climate change. And that's this shaded band right here. That's the range of natural variability. But if you look at the red line, which is the carbon dioxide concentration of the atmosphere since the Industrial Revolution, today it's sitting here at 390 parts per million. And if there's no change in human energy generation, then by the end of the century, it's going to be up here. And that has, as I say, profound impacts on the ice of the Earth. Now, some scientists say that if we could adopt measures that would hold the increase to no higher than 450 parts per million, that we might forestall the worst of the changes to the cryosphere. We might not lose so much ice. We might not see such dramatic changes of sea level. But we're at 390 today, and 450 parts per million is that kind of ceiling that people are urging us not to penetrate. But at the rate at which we're pumping carbon dioxide into the atmosphere, between 2 and 3 parts per million every year, you can do the arithmetic. There are 60 parts per million to work with, and at 2 to 3 parts per million every year, that's 2 to 3 decades that we have to totally reverse our energy consumption away from the fossil fuels and into renewables. So with apologies to my physicist friends who often will tell you that the Large Hadron Collider that began business in Switzerland a year or two ago, they would often describe that as the largest experiment ever conducted by humans on Earth. And I would argue that that's not true, that the largest experiment conducted by humans is what I call the big inadvertent experiment with Earth's climate that we have unwittingly undertaken when we decided to utilize fossil fuels for the energy of our industrial economy. We didn't do it with malice, we didn't do it with carelessness, we just did it, and we're now realizing, of course, that there are consequences to that. And the way in which we respond to those consequences, the way in which we respond to the big changes that are coming if we don't respond, is a real test for the maturity and of the political systems of the globe. So the last slide is this. The Chinese word for crisis is actually 2 words, danger and opportunity. And I've talked a lot about the dangers, but there are opportunities as well for humans to remake the modern industrial economy by moving away from carbon-based energy into other forms of energy. That's the real challenge of the 21st century. And it's not without its difficulties, but one should consider it as an opportunity. And the countries of the world that seize that opportunity are the ones that will be the leaders of the 21st century. And those that are hesitant or decide to stick with the status quo, they will be the also-rans of the 21st century. Winston Churchill once defined a pessimist as someone who saw the difficulty in every opportunity. But an optimist was someone who saw the opportunity in every difficulty. To be sure, we are looking at a lot of difficulties, but I think we should all be Churchillian optimists and recognize that there's tremendous opportunity in the difficulties we face. Thank you very much.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.